Hello, welcome to section 2.1. What we're going to do is model linear situations. What that means we're going to do is identify what our quantities are as far as the input value, the output value, independent and dependent quantities. We'll talk about units and rate of change. So I'll kind of just jump into this first part here. It says identify the independent and dependent quantities in each problem situation, and then we're going to write a function to represent the problem situation. So we're going to be using this function then. We can use it when we put inputs into the function, or I can give you an output and we can solve for an input. So we're going to do a lot in this lesson. So we're going to do this and write a function for each problem situation. So the Booster Club for football sells hot chocolate during varsity football games, so that happens here. Each cup of hot chocolate costs $2. So let's think about what our independent and dependent quantities are. So again, you're thinking about the club is selling the cups of hot chocolate. So we have cups of hot chocolate and it's costing $2. So the independent quantity is going to be the number. If you think about it, they're just going to be open for business all day. It's the number of cups they're going to be selling. So number of cups of hot chocolate. And then my dependent quantity then would be the total cost. So if you think about it, if they sell 10 cups of coffee, well, it's 10 times 2, so that'd be $20. If they sell 50 cups of coffee, it'd be 50 times 2, so it'd be $100. So I know that whatever our input value is, we're going to be multiplying that number by $2 for every cup it is, and then it'll give me my total cost. So to write a function for this, first of all, let me define variables here. I'm going to use the letter C for the number of cups, and I'm going to use, I'll just say a letter F for the total cost. So what I would do is say F of C. That's how we write our function. So we're going to say this F represents my total cost for every number of cups, and that would be 2C. So we know that however many cups of hot chocolate they sell, you would just multiply that by 2, and that would give you your total cost for it. And again, notice I'm just using any letters here for the variable. Doesn't matter. C works for cups. F has nothing to do with cost. It's just a letter, and that's kind of the beauty of variables. Next one, Basketball Booster Club sells t-shirts at the varsity basketball games. Each t-shirt is costing $12. So my independent quantity, it's kind of like how the last one goes. If you think about it, you can't buy like 1.5 shirts. They're selling like whole shirts. So it's the number of shirts that they sell. And then very similar to the last one, your dependent quantity again is going to be the total cost. Or you could even say it's, instead of saying cost, it's kind of like the income, because you're thinking about it, the Booster Club is selling them and then they're getting that money. So I'm going to use the letter S for my number of shirts, and I'll use a big capital C for my total cost. And then just like how the last function looked, it's cost as a function of the number of shirts, and that would equal $12 per shirt. So notice the variable that you're lining up here on the inside of the parentheses is your independent quantity, and you also see that in the equation as well, and that same thing happened down here as well. So your independent quantity is the one that, and you think about in both of these cases, that the booster clubs are controlling. They're controlling how many shirts they sell, and then whatever number of shirts they sell, the cost will depend on that. Next one. So now we're going to kind of take what we just did in the last problem and make a table out of it. So we're talking about volleyball now. The volleyball boosters sell bags of popcorn during varsity matches to raise money. So very, very similar to the last two examples. They're going to be selling popcorn this time. So bags of popcorn. So the independent quantity, again, it's going to be that number of bags of popcorn they're selling. So I'm going to put number of bags of popcorn. And again, just to kind of clarify this too, I don't want to just put bags of popcorn because I don't want you to think that the price is a variable. It's the number of bags that they sell. My units on this would be however many bags it is. And the expression that I'll use will be a letter B. The quantity that's going to be dependent then, if you think about it, if they sell 10 bags of popcorn, 20 bags of popcorn, 50 bags of popcorn, you would multiply it by 3, and that would give you your total cost. So again, I'm going to put total cost here, and cost would be measured in dollars. And then my expression, if you think about it again, we're just taking $3 times the number of each bag. So if B is the number of bags, 3 times B would represent my total cost then. So we'll fill in the table from here. All that you're doing is taking the 5 basically and multiplying it by 3. So what you're doing is you're taking the 5 and you're substituting it in for the letter B here. So 5 times 3 means this would be $15. 10 times 3 would be 30, 15 times 3 is 45, 20 times 3 is 60, and 25 times 3 is 75. And again, that would represent dollars. So if they sold 25 bags of popcorn, it would give them $75. These ones, we're going to do input value, output value, and rate of change. It's going to work very similar to what we did for independent and dependent. We're going to have input and output values. And we're also going to identify the rate of change here, and we'll talk about what that means. So in this first example, we're talking about a person that's driving 65 miles per hour visiting a college campus. Here's your function, d of t equals 65t. And it represents the total distance traveled as a function of time. So I want you to imagine this person's getting into a car and just starting a stopwatch, and they're just going to drive, and as soon as they pull over their car, they're stopping that stopwatch. So what are they controlling? Well, they're controlling how long they're driving. So what that means is that my input value, my independent quantity here, your input value is going to be time. And in this case, it's going to be measured in hours. And then my output value. So if he drives for 2 hours and he's going 65 miles per hour, it'd be 65 times the 2 hours he's driving. That means he would be driving 130 miles. So the output is going to be his distance. And that distance is going to be measured in miles. And if you think about it again, what your rate of change is going to do is it's going to relate your two variables to each other, or the two units. So it's going to be miles per hour. So my rate of change in this case is going to be the 65, and that is going to, again, it's telling you how many miles he is traveling for every hour. So it's comparing your two, that's what I'm thinking of, it's comparing your two units on both of your quantities. So my rate of change here is going to be 65, and again, it's miles per 1 hour. Alright, next one. So Kiana is selling coupon books to raise money for school. Each book costs $35, and here's the function again. So M of B equals 35B. So they're saying that the money raised is going to be the letter M, that's our dependent quantity, and the B is going to be the number of books that she sells. So I think we've all been out going door to door selling wrapping paper, something like that, and you're trying to reach a goal. So you're the one that's going out there, you're controlling how many items you are selling, and then however many items you sell, your money that you make depends on that. So my input value here is going to be the number of books sold, and that would be measured in books. So she sells 10 books, 20 books, whatever it is. And then my output value here, again, that would be the total money raised, and that would be dollars. So again, I want you to kind of draw this comparison here. What the rate of change is going to do is it's going to compare your output unit to your input unit. So in the last example, we had miles per hour. In this example, we're going to have dollars per book. So my rate of change here in the problem is the 35, and again, that 35 represents the number of dollars, $35 per one book. So a good way to make sure that you know what your input and your output are, when you look at that rate of change, make sure that it's comparing your output unit to your input unit. So it's dollars per book. It's not books per dollar, it's dollars per book, and in the last example, your speed would have been miles per hour. What we're going to do for these ones is solve a function. So what I'm going to do is give you the input value. So that would be like in the last example, I would tell you how many books she sold, and then we'll solve for what the output value would be, and that would represent kind of like what the total cost would be. So this is talking about the money that somebody is earning while babysitting as a function of time. So this person's controlling how many hours. So what I'm going to do here, since it says A of 5, A is going to represent the total amount of money. 5 is going to be my input value here. So she controls that she worked 5 hours, and we're going to figure out how much she made. So what you would do is say A of 5 equals 7 times 5. So what you're doing is, again, I'm lining up these independent variables here. My input value here is T. T represents the total number of hours that she worked. So if she works 5 hours, 7 times 5 means that she made $35. For this one, this would represent that she worked 4.5 hours, so 4.5 hours. So you would do it the same way. A of 4.5 equals 7 times 4.5, which is going to come out to 31.5. And that means she would make $31.50. And one of the things I want to kind of clarify with this too is that whenever you finish these problems, you do not have to do anything at the very end of this left side. So what I mean is you're going to bring A of 5 down. What this means is for every 5 hours she works, she makes $35. For every 4.5 hours she works, she makes $31.50. So you don't want to do anything else with the left side. The point of doing that, again, is you're being able to see your input value is 4.5, your output value is 31.5. And then the last ones. What we're going to do is use a graph now to determine what the input value is, and I'm giving you the output. So we're working backwards from the ones that we just did, and we're going to use a graph to help us with this. So it says the function d of t equals 40t represents the total distance traveled in miles as a function of time and hours. So if your distance as a function of time equals 40t, if you think about it, if the person travels 2 hours, that means that'd be 80 miles. And if it was 3 hours, that'd be 120 miles. So the 40 is going to represent the rate that they're traveling. So the 40 represents the miles per hour. So that's the speed they're traveling at. Now, this is saying d of t equals 240. So think about this. I'm giving you the output value. So I'm giving you 240 miles, and we want to know how many hours she's traveling. So I'm not going to look here first. I'm going to want to look at the y-axis because this is the one that has the 240 miles. And what you're going to want to do is find where the 240 is, and we're going to draw a straight line over. And we're going to find that intersection. Crosses my function line here, and then we'll go straight down, and we can see that it would be 6 hours would give me 240 miles. So what you would do is say t equals 6 hours. So if the person travels 6 hours, they would be at 240 miles. And then I'm just going to move these out of the way. And the next one would be 80, so I'm going to do the same thing. I'm going to find where 80 is on here. We're going to connect going over to our function line. This diagonal line is our function. And I'm going to trace down to my x value, so that's 2. So what that means then is that after 80 miles, I know that my time would represent 2 hours. And that kind of makes sense if you think about it. They're driving 40 miles in 1 hour. So then that would be 80 miles in 2 hours, and that would give you that point right there on our line. And notice every time they travel a certain time, they would be at a certain distance. So each one distance means that you would have one time associated with it. Alright, so just to kind of quickly recap everything that we did then, we talked about independent and dependent quantities. We filled in a table, we did input and output values and identified what rate of change was, and then we evaluated functions with input and output values.